Okay, so we will talk about this Legendre and Jacobi symbol, which is based on the what is we have seen the quadratic residue. So, let us just recap the what do we mean by quadratic residue. So, this definition you have already seen. So, let P be a prime and an integer A is called, this we have seen, just to recap, called a quadratic residue modulo P if it has a square root. That means, if y square is equal to congruent to A mod P has a solution in Jacobi. That means, if there exists a y 0 less than y less than equal to P minus 1 such that y square will give us A. So, that means, we should able to square root the find the square root of A, then it is called a quadratic residue, and we have seen some result on the quadratic residue like by Euler's result. So, the Euler's theorem is telling, Euler's criteria is telling, if a to the power p minus 1 by 2 is congruent to 1 mod p, where p is a prime, then A is a quadratic residue mod p, quadratic residue mod p. So, this result we have seen. So, this result we have proved. Okay. So, now today we will talk about, before defining this two symbol, let us talk about how many quadratic residue and quadratic non residue are there in the A over P. So, say this is the this is by theorem. This theorem is telling, let P be a prime number. So, we are not considering 2. So, this is a odd prime, okay. And then if we denote the QR, basically is the quadratic residue class, QR is the QRP, we denoted by QR. This is the set of quadratic residue mod P, and QR P bar is the set of quadratic non residue mod P. Then this theorem we want to show that these two sets are same, cardinality of these two sets are same. The number of quadratic residue is same as number of non quadratic residue. Okay, cardinality of these two sets are same. So, we will prove this theorem. So, before prove this theorem, let us take the example. So, suppose P is equal to say 5. So, P is equal to 5, who are the quadratic residue? We can easily verify that. So, for P is equal to 5, the quadratic residue are basically 1 and 4, and the quadratic non residue are basically 2 and 3. Okay. And say for P is equal to 7, we have quadratic residue are basically 1, 2 and 4, and quadratic non residue is 6. This can be easily verified. P is equal to 11. This example we have seen 3, 1, 3, 4, 5, 9 and quadratic non-residue are basically quadratic residue minus that set Zn, I mean here Zp. And for P is equal to 11, 13, these are the quadratic residue 1, 3, 4, 9, 10, 12 and then these are the quadratic non-residue. Okay. So, these sets are equal. So, that means if we take a prime P, then the number of quadratic residue over Zp over this modulo P is same as number of non-quadratic residue over P. So, how to prove this? So, to prove this, so we will show basically this set, if we consider this set 1 square, 2 square up to P minus 1 by 2 whole square mod P. So, these sets will give us basically QRP. Every operation is under mod P. These are basically give us the QRP, quadratic residue. And so, how many number of elements are? Basically P minus 1 by 2. So, what we need to show? We need to show that any two elements in this set are distinct, then we are done. So, let us take two elements from this set x square and y square. So, suppose they are not distinct, suppose x square is congruent to y square mod P, where x or y both are coming from 1 less than x less than P minus 1 by 2, 1 less than y less than equal to P minus 1 by 2. Okay. Now, from here we can say x square minus y square is congruent to 0 mod P. So, this implies x minus y, x plus y is congruent to 0 mod P. So, this implies x must be congruent to x equal to y basically. So, that's the proof. So, this means if you take two distinct x y, then they are not same. So, this completes the proof. So, the number of element in the quadratic residue are basically this set, and then so there are P minus 1 by 2 elements in this set, and so the remaining elements basically are the, so QR P bar is basically ZP star minus QRP. So, the cardinality of this set and this set are same. So, this is the proof. Now, we will define what is called Legendre symbol. Okay. So, Legendre symbol is basically defined as this. Let P be a prime. For Legendre we need P to be prime, be a prime number, and A be any integer. Okay, this is definition of the Legendre symbol. Then we define A by P like this. This is the Legendre symbol. This is the symbol, Legendre symbol. This is how we denote the Legendre symbol. So, this is basically have possible three values. It is 0 if A divides P, okay, if A divides P or P divides A, and it is 1 if A is a quadratic residue mod P and it is minus 1 if A is a quadratic non-residue mod P. So, this means A is a quadratic residue mod P, this means A is a quadratic non-residue mod P. So, it can take 3 possible values, and but we have to be careful where P this for Legendre this P is prime. So, Jacobi we will see, Jacobi is the general form where P need not to be a prime, P could be any integer. So, we will see this Jacobi symbol later on, but for the time being we are talking about Legendre symbol. For that we need P must be a prime, and this is defined by this functional form. So, it is 0 if A divides P. So, say if A is equal to 2 P or 3 P like this, then otherwise if A is not divides P. So, then it is 1 if it is quadratic residue mod P, it is minus 1 if it is quadratic non-residue. Okay. Now, we will talk about some result based on the Legendre symbol, or you can say theorem. Okay, first theorem is by again by Euler. So, this is telling this is the theorem again from Euler criteria. So, it is telling that A by P is congruent to A to the power P minus 1 by 2 mod P. So, A to the power P minus 1 by 2, this is P minus 1 by 2 mod P. Okay. So, if we have this, then we can calculate this, because if we can calculate this symbol, because this is just the exponent. Okay. So, now how to prove this theorem? Okay. So, to prove this theorem, so if A is congruent to 0 mod P, that means A is a multiple of P, then we know A by P is 0, and also it is easy to show that in this case A to the power P minus 1 by 2, this is also mod P, this is also 0. Okay. So, when A is A divides P basically. So, this is case 1. Now, suppose case 2, suppose A does not divides P. So, in this case what we will do? So, in this case this Jacobi symbol, a Legendre symbol is either 1 or minus 1 depending on whether this is a square root or not. So, in this case what we will do? We will take this A minus P by 2, we square it up. So, this is basically give us A to the power P minus 1. Now, this we know by the Fermat's Little theorem, this is congruent to 1 mod P. So, this is case 2. So, this implies either A to the power P minus 1 by 2 is congruent to 1 mod P, or because this is 1, square of this is 1. So, this guy is either 1 or it is minus 1 mod P. Now, we know this is 1 if A is a quadratic residue. So, we know this is, if this is 1, then A is a quadratic residue mod P, and in that case if A is a quadratic residue, then A by P we know is 1. So, that means A by P is same as A to the power this. Now, if it is minus 1, then this implies A is quadratic non-residue mod P, and in this case it is minus 1. So, in this case we know by definition of Legendre symbol this is minus 1. So, if we combine these two and the earlier case this is the same as. So, A by P is equal to a to the power p minus 1 by 2 mod p. So, this is the theorem or this is a result. So, this result will help us to calculate the this Legendre symbol of some numbers. Okay. So, this is the proof of this theorem. So, we will use this theorem to calculate this. So, let us have few more theorems on this. So, yeah, so let us suppose p is prime. So, and m n are two integer. So, m n p is n by p, okay, where m n are two integer, where m and n are any two integer, but here p is a prime. So, so far we are taking p prime, this is mandatory because this is the Legendre symbol. Okay, so, how to prove that? So, to prove this, suppose p divides yeah. So, how to prove this? Suppose p divides m n. So, if p divides m n, this means m n by p is 0 and p divides m n means either p divides m or p divides n. So, that means either m is a so if this is the case, if p divides m, that means m this is 0 or this is 0. So, in any case either of these two is 0. So, that means this product is 0 and we have this 0. So, this is a when p divides m n. Now, if p does not divides m or n, then we will use the Euler's theorem to prove this. So, suppose p does not divides m and p does not divide n. So, that means then p does not divides both m n. Okay. So, in this case m n by p is basically we will use the earlier theorem, Euler's theorem. So, it is basically m n to the power p minus 1 by 2 mod p. So, this is basically m to the power p minus 1 by 2 into n to the power p minus 1 by 2. So, this is basically m by p into n by p. So, this proves this theorem. Okay. So, this is the if we have product m n, then it is basically product of the individual Jacobis. Okay. So, now another theorem which is coming directly from the Euler's result. So, this is telling minus 1 by p is basically, so you can take this off, minus 1 by p. So, that means a is minus 1 is basically, so this is by Euler's criteria, this is basically minus 1 to the power p minus 1 by 2 mod p. So, this is basically 1 if p is congruent to 1 mod 4 and it is minus 1 if p is congruent to 3 mod 4. since P is prime, so P is either congruent to 1 mod 4 or P is congruent to 3 mod 4, either one of these, because other two option like 4k and 4k plus 2, those are not give us P prime. So, this is basically P is, so if P is, so from here if P is congruent to 1 mod 4, we can put this value and we will get 1, and if P is congruent to 3 mod 4, it will give us 4. So, this proof is also straightforward. So, now the next result, so this result we will be using for calculating the Legendre symbols. So, next result is telling us 2 by P. So, 2 by P, here P is a prime, because these are all Legendre symbols, is minus 1 to the power P square minus 1 by 8. Okay. And this is basically 1 if P is congruent to plus minus 1 mod 8, that means P is congruent to 1 mod 8, and this minus 1 means P is congruent to 7 mod 8. Okay, or, and this is minus 1 if P is congruent to plus minus 3 mod 8, plus minus 3 mod 8. So, that means if P is congruent to 3 mod 8, and for minus 3 it is basically 5, or P is congruent to 5 mod 8. This also can be proved, this theorem. So, this is basically telling us 2 by P is basically minus 1 to the power this. So, if P is either of this form, then it will depend, just we can put the value of P here and we will get either 1 or minus 1 there. Okay. So, next we will define what is called Jacobi symbol. So, it is a generalization of the Legendre symbol, where this, so far we have assumed P is prime. Now, what happened if P is not a prime? Then how we define this symbol? So, that is called Jacobi symbol. So, this is defined for any integer n. So, let n and a be any integer. Okay. Now, if n is an integer, so it is either a prime. If it is a prime, we have the Legendre symbol, or if it is not a prime, then it must be written as the product of the prime. That is the fundamental theorem of arithmetic. So, n must be written as P1 E1, P2 E2, P3 E3, PL EL, product of prime. Then this is the definition of Jacobi symbol. We define A by n is basically A by P1 to the power E1, A by P2 to the power E2, like this, A by PL to the power EL. So, this is the definition of A by n, where n is not a prime. Okay. So, for example, suppose we want to, for example, suppose we take n is equal to 21 or say 63. Yeah, for example, n is equal to, okay, 21, simpler one. So, 3 into 7. So, 3 7s are prime. Now, a by, so n, a by 21 is basically defined as a by 3 into a by 7. Okay. So, now if n is equal to say 63, so this is basically 3 square into 7. So, a by 63 is basically defined as a by 3 square into a by 7. Okay. So, this is the Jacobi symbol is defined through the Legendre symbol, and so now we will talk about some properties of this symbol, so that you can use this to calculate the Jacobis or yeah. So, these are the result on the Jacobi symbol, and this can be proved by this factorization of the primes in Legendre symbol. So, these are the properties of Jacobi symbol. Okay. So, like this first property we can write this a b by n is equal to a by n b by n. So, this can be proved from that Legendre symbol theorem. We have seen this type of result in a Legendre symbol. Okay. Now, a by m n is basically a by m into a by n. So, this also we can prove, and if a is congruent to b mod n, if a is congruent to b mod n, then a by n is basically equal to b by n. So, this similar proof we can do it for when n is prime. That proof is coming from that Euler criteria, but this can easily prove if a is congruent to b mod n, then a by n is equal to b by n. So, another result could be, so 4 minus 1 by n, this we have seen, minus 1 to the power n minus 1 by 2. So, 5 is 2 by n is equal to minus 1 n square minus 1 by 8. Okay. So, now we have a reciprocal theorem. So, n by m or m by n is equal to n by m to the power minus 1 to the power m minus 1 into n minus 1 by 4. So, these are the theorem or result. This can be easily checked by using the factorization and then the Jacobi symbol. Okay. So, this is either 1 or minus 1 depending on this value. So, if it is so this is mostly m by n is equal to n by m, mostly it is there unless both m and n are congruent to 3 mod 4, are congruent to 3 mod 4. Unless this, we have this result. So, they are reciprocal. So, we will use this result to find out the Jacobi symbols of any number a by n, and we will see how it will be useful for have a crypto system or for the primarity testing to check whether a number is whether n is prime or not. Thank you.